yell a bit. Okay. All right, so welcome to this afternoon session. I know you have a really full agenda. I was very impressed with the scope of the 2 days here, so it's great. This one, I hope this is an easy hour for you in some sense, because it's supposed to be. Okay. My name is Barbara Chapman. I'm from the University of Houston, as you see in the first slide. And I'm actually using a set of slides that has been created by Brett Estrade, who works for me in Houston. So I've left his name there to acknowledge that. He's actually still finalizing a set of slides that's much longer than the one I'm going to use here today. And I believe you're getting this as a handout, but you may want to make a note of this. This link down here is actually the link to a lab website there, so it's more than just OpenMP stuff. But if you go there and look at the top of there is a link to that says Open. I think it just says OpenMP on it, and these slides, or the superset of these slides, is there too. So feel free to go there sometime soon and download that and get a somewhat more extensive version of these slides, along with some more application examples. So there's some more stuff there, and there are references to some other kinds of slides and benchmarks and other things if you'd like to grab those. So that's a few more resources. Okay, I've been involved with OpenMP not quite from the start, but from its infancy, I would say, and I've been part of the language committee there for quite a few years and the administration committee in more recent times. So know quite a bit about the history of OpenMP, and I'll try to maybe say a few things about that as we go along too. Okay, now I just have to figure out. Okay, just click on this one. Okay, so I think you've been talking about shared memory systems already this morning, so you had a discussion of Pthreads. So I'm going to try and set the scene. So what I'm going to do, how many people have used some OpenMP at any stage or tried stuff out? Quite a few, okay. For you, this may be a little bit simple, so just relax, okay? If I forget something important, you're even allowed to help. Okay, that's right. So these are sort of fairly introductory slides, so as you probably know that there are some tricky parts to OpenMP too. Okay, so OpenMP was designed to be an application programming interface for shared memory systems. So in other words, it relies on the availability of shared memory to allow different threads running on different cores or processors in the system to interact. Right? So they're all supposed to work on to solve a particular computational problem. They interact via shared memory. OpenMP has been implemented on machines that actually have distributed memory. That has been done very well on systems such as SGI's Origin and the Altex, where there is in fact system support for global memory addressing. In other words, there's real system support for treating it as a big shared memory system with some disparities in the access time that you take to reach some memory. It has done very much less well on distributed memory systems that do not provide that kind of support. So if you have a cluster, could you implement OpenMP on a cluster? Yes. Can you do it well? Well, it's pretty darn difficult. There have been attempts to do that. Intel even worked very hard on a product that is, I believe it's still available, but most people agree that that's actually very hard to do and will take a lot more work if people want to do that in the future, which is quite possible. So it's not something that's dead, but it is a very difficult problem to get this to run well on a true cluster. Okay, and as you probably already know, even on a shared memory system, there is some memory that's actually not really shared, and that's cache. So it's sort of kind of hinted at in this particular slide. And that occasionally causes some problems. You have to actually know that that's the case to understand a few of the things that can happen, particularly that may cause problems with OpenMP. So we'll come back to that. Oops, I'm sorry. For some reason, I'm not seeing the changes on the screen here, so I zapped past it. Okay, I'll just look at this one. Okay, so what does OpenMP do? How does it work? So we're going to spend a few slides just setting the scene and trying to understand what OpenMP is in the first place. So this is as good a place to start as any. So assuming that you have a shared memory system with a bunch of CPUs, You can think of an OpenMP program has a single process and a bunch of threads. And those threads, again, will share memory. So they're all using the same address space. They can use the shared memory to, in fact, collaborate to do their job. When an OpenMP program starts, a thread is started somewhere on the system. So there's nothing magical about the CPU 0 here. That's, perhaps it shouldn't even have had a number here. Somewhere on your shared memory machine, a thread will be started. In OpenMP speak, we call that the initial thread. It's the one that's getting things started. When that thread encounters a parallel region, you as a programmer will tell the system essentially when you want to run things in parallel. And it could be right away. All right? That would be a great program if it was right away, because then you wouldn't have too much sequential code or too much before you actually really go parallel. At that point, there will be some new threads forked to execute the parallel part of the code. Right? So those threads start up. They're executing in the same address space. All of those threads are going to do some work. Ideally, or this is again an ideal setup, we've got each thread on a different CPU. Usually you would like that in an OpenMP program. Most systems would strongly prefer you to have each thread running on a different resource. They're all going to do some work. When that parallel region or that parallel part of the program is finished, they join. So we call this a fork join model. So they all come together. All but that initial thread terminates. Right? So the other threads stop executing. They are out of the picture. And the thread that created these other ones, the thread that actually was there before the fork, continues. The other name that we give to that thread, by the way, is the master thread. Because when you start up this parallel region, if you notice here, this one is actually going to continue working. It becomes part of that team. So we call this the team of threads that's executing the parallel region. And this thread here is the master of that team. And it always has a thread ID of 0, so you always know which one is the master thread. It's the lead guy. Although, in fact, in some sense, most of the time when they're doing work, they're all equal partners in it. They're all ideally sharing and doing exactly the same amount of work. So the master is perhaps not the best term, but it's the one that keeps going at the end as well. Okay, so OpenMP is not a standard in the sense of C or Fortran. It is an industry standard, which means that it has a specification that is, in fact, very carefully managed by something with a rather strange name. It's called the OpenMP Architecture Review Board. The members of that OpenMP Architecture Review Board are mostly companies. There are also some organizations, some universities. This is not all of them here, but I put some of the ones that you probably know. There are hardware companies. There are some compiler companies, so software houses. There are a couple of government labs, as you can see here. NASA's a member. There are some universities that I did not list here. Compunity is a research organization. It's a collaboration of researchers that I actually founded so that we could be part of this development effort. So there are some researchers who worked very consistently for pretty much the lifetime of OpenMP as well. So it's not just industry working on it, but it is pretty heavily dominated by industry. And this Architecture Review Board has not only designed, if you like, the standard, come up with the specifications, it is very actively debating them. So if you have questions or problems with using OpenMP, and people do, of course, or you don't understand how something works, or you've come up with something that appears to be maybe ambiguous in the specification, you can write to these people, and your comments, questions, queries will be reviewed and responded to. If it's that kind of an issue, or if it's something where you think you found a problem, people will talk about it. So those things are not ignored. Another very good place to look for resources on OpenMP is the official website for this Architecture Review Board, and that's this line here. So you can access the specification. So, I don't know how many people here sort of like to read the C reference manual before breakfast, right? Just kidding, right? It's not great bedtime reading, right? It's sort of the OpenMP specification originally was designed to be very easy to read. So that users, people who actually want to use it rather than implement it, could read it and understand it. So over a time, of course, the people who were trying to implement it wanted more precision and more clarity, so that they could read it too and get the information that they need. There was kind of an attempt to do both in one document. That unfortunately makes, so when you try to be a bit more precise about things, or ideally really precise, that's what implementers need, that it's hard to do that and be very readable at the same time. So people have tried pretty hard to do that. I think compared to a lot of language standards, they've done a good job, but it had to become a bit longer as a consequence because there were more exceptions, more kinds of rules. But it is still pretty accessible. So you can go there and get the specification and look at it, and it is a good idea to have it. So it's free, of course, you can just download it. It's a good idea to have that to go and look up, especially if something doesn't seem to be quite working out. So it's probably not a good place to start, but it is good to have that and to check things up and to see whether, if you have a problem somewhere, whether there is a rule that you violated, and may come back with that. And they also have some resources, so it's a good place to go. Okay, but what is OpenMP? So it's a programming interface for shared memory programming. We've said that. It is something that's really, truly designed to run on shared memory. How does it do this? Well, it's a set of directives. So if you've been discussing Pthreads earlier today, OpenMP is somewhat different from Pthreads. There is a bit of overlap, actually, in functionality, or at least in things that you can express. But it is designed to be much simpler. So obviously, there are quite a few different programming languages out there for different purposes. There are different, what we call design points. So when you're creating a programming language or a programming interface of some kind, you have a certain set of goals, and there are trade-offs that we all like to talk about in terms of what you can do with a particular programming interface. And OpenMP, in the spectrum of programming, it's the interfaces for shared memory programming, tries to be fairly simple and tries to be easy to use. All right, so I'm sorry, that's sort of saying something. Tries to be easy to use, but simple in terms also of not having too many different features. Okay, so it hopes to be make life, let's say, easier than something like Pthreads when you're writing a program, and in particular when you are maintaining one. So we often forget about the problem of actually working on a program after you've got the initial version. So that's everything that happens, particularly in industry, of course, where a code could be fairly large. And somebody else has to come and work on something and add some features. How easy is it to understand what this program is doing? How easy is it to make changes? And that can be important, right? So OpenMP tries to facilitate those kinds of users who would like to have something that's reasonably easy to use. What that means is that in terms of choices, the implementers there have sometimes not implemented things that are perhaps doable, but regarded as making it perhaps a little too unwieldy. And so there may be some things that you can't express very easily using this interface because it's designed for certain things. So you have to look at the features and see how it can help you as well. Okay, so without any further ado, we'll start looking at a few. Okay, so this is just to help us get started. And we're going to do some things using some pretty simple examples here. So I'm trying to sort of show you what the main features are and what the flavor is. And again, if you have used this at all, you'll find this pretty easy. So I hope this will be just a nice review session for some of you. Okay, so OpenMP uses directives, which are comments. We'll go back to that in a moment. Well, arguably the most important of them is the parallel directive, because unless you as the programmer say, I want this part of my program to run in parallel, everything will be sequential. Right? Remember, one thread starts up executing, and unless you do something, only that thread will do some work. So you've got to have a parallel region to give this some teeth, some power. So we're using a C code, so we're inserting this into a C program here. And this line, this pragma, says OpenMP parallel, so that again, that first thread will be executing will now fork some threads to execute the work inside here. So that directive is telling the implementation to do it. And note that you don't have to say all the details here. You're not forking all the thread explicitly. You're saying, do this for me. Okay, so here's the trade-off. The implementation has to do that. The parallel region that, or the part of the code now that's going to be executed in parallel has to be what we call structured. That means we don't do anything fancy in here. We don't try to jump into a parallel piece of code or jump out of it or in and out or anything like that. People have tried these things sometimes in the past, but OpenMP pretty much forces you to think in it, to write fairly structured programs. So this part within that's governed by the pragma, so this here in C is pretty easy to see with the braces, will be executed by the threads that are forked. All right. At the start here, so OpenMP also has some runtime user functions that you can call. There are not a lot of them. They're pretty powerful in terms of what you can do with them. So even though they're very simple, they can be pretty darn useful. This one here is just simply saying get the number of threads that will be used to execute this parallel region. So typically you will try to set that yourself, and we'll see how to do that in a moment. All right, so there are some functions, simple but quite powerful. The directives have some clauses. You can use those clauses simply just to give extra information to the system or perhaps to set conditions on the execution. We'll look at those in a moment. And we have some other kinds of directives, some standalone ones. The barrier we'll come back to because it's pretty fundamental. So that you've seen just about everything you need to see in an OpenMP program. We have some directives, one or two that are really critical. Those directives can have additional information with them. There are some user-level functions that you can call to help control your program or to get information. In fact, there's something that's outside of the program that we'll mention too, some environment variables. Okay, so again, OpenMP is something that you add to a program that was written using C or C++ or Fortran. Most work that I have actually seen in the past has been with C or Fortran programs. I think people are starting to use it more with C++ now. Initially, OpenMP was designed to work with Fortran. Then it was extended to C. Then those initial standards, initial hacks, initial attempts to provide something of this kind were extended somewhat. And then in 2005, we came up with a revised standard, which would say, here's the standard, and here are the bindings for the different languages. The reason for that is that people didn't want the two bindings, the one for Fortran and the one for C, to be out of sync all the time. They wanted them to really be the same. So if you're writing something in Fortran, you should get the same features as in C. Sometimes it's hard to do things for both languages, right? So Fortran and C are obviously not identical. It can be hard to express things in both language sets, but the goal is there to do that. And this so it was called 2.5 because it wasn't really new. It was a merger of them, and did a much better job at explaining some of the features. We are up to 3.0 now, so the official version is 3.0, and there is a draft of 3.1 which has a few minor changes in it, so minor extensions. And we are working on 4.0, so there are still things going on, a lot of things going on actually in the community. So try to find just a couple of minutes to mention those at the end. Okay, so why might you be interested in using OpenMP? Well, these are, I don't know if this is the right order to talk about things, and I'm sure there are lots of other potential reasons too. One, of course, is that even though it's not a standard in the same sense as C, it is an industry standard. There are a lot of compilers out there, so you can run an OpenMP parallel program on most systems. If you have a GNU compiler, GNU has OpenMP in it too, so the chance that you have a system with no OpenMP compiler available is very low. Depending on your code, sometimes it's really easy to use OpenMP, right? I actually interacted one time with somebody in a company in Italy he was really happy guy. His company had a product. There was a database that was used a lot in the government there, and he added some OpenMP to their systems, to their software, apparently with great ease. So it was just a very simple addition in this case. What his boss saw was that all their stuff suddenly sped up and all their customers were real happy. So he didn't sort of tell them that this was a trivial piece of work. And it looked like an amazing change to his boss. So it's you can sort of cheat with us sometimes too. Of course, a lot of us here will be researchers and we may have complicated code and it may not be that easy. But sometimes it is. The other thing that can be helpful when you're using OpenMP is, or actually doing that first port, if you like, is that you don't have to create a complete parallel application right from scratch. You can start to work on it. Depending on your needs. So again, there are very big variety of different kinds of users. So some people really want to squeeze every last piece out of an application. We often think in research that that's what you've got to do. Some people don't need to do that. So sometimes in industry you have a certain requirement. You need to meet a certain kind of speed. And maybe you can take a piece of your application, create or an OpenMP version of that, and you're done. So that happens, right? So it really depends. Sometimes that makes life real easy. Again, sorry, I forgot what I was going to say there, but just coming back to this one. One of the things that's important for OpenMP, and I saw this in the title or description of your presentation this morning that said something about how you need to know about the hardware. OpenMP is somewhat sensitive to the way your program is using memory, and it's good to understand what the memory hierarchy really does look like. So if you're not getting the performance you need, it's good to think about how cache in particular is being used, how are the threads accessing memory, and working on that can help. Of course, it helps your sequential program too, so it's just a good idea to be very aware of the way that your program is using memory, and to work on that. Okay, so immediate gratification, of course, is referring to the fact that sometimes you can actually create an OpenMP version quite quickly. Okay, so OpenMP is providing or it provides some directives, some structured comments that you can. Was there a question? No.
So is this something that, let's say you're writing a large commercial kind of application for a Mac PC or something? Is OpenMP something that people actually use to move it to 2, 4, and 8 cores?
Yes.
Today?
Yes.
Okay, so this is fairly commonly used in
Yes. Yes. Yes.
What would be the biggest objection that an application developer would have against using OpenMP to move to multicore?
Actually, that's a really good question. So these things always have trade-offs, right? And there are certain things that you can't do with OpenMP. So in particular, if you think about Pthreads and the ability of a thread, this is just off the top of my head, there's probably better arguments than this, but one thread can destroy another one and so on. You don't have those kinds of options in OpenMP. OpenMP has a certain range of features that are useful for a lot of applications, but not for every application. So there are some limitations in that sense. The other one is in terms of really getting great performance. And this is actually true, I think, for most high-level programming models. When you use directives, sometimes you think, well, here's my program. I've got 100,000 lines. I add 3 lines here, and I'm done. All right? There are times when that actually works. Right? There have been spectacular stories, and this database one was one of those where a tiny bit of work was quite enough. But there are many times when that doesn't work, and that's because it may work in parallel, but it may not give you the performance you want. And then you may have to do some extra work to get something that actually works, not just works in parallel, but works in parallel and gives you the desired speed up, depending on what that is. And actually, if we go back to the previous slide, that typically has to do with the way your memory is being used, right? So what I would say is it's a fallacy to think that you can use OpenMP and just add 3 lines and everything is great all the time. It sometimes works. But typically you have to think about how your memory is being used, and that means you may have to do more work to get to that initial parallel version, right? The thing that I think people tend to forget I have not seen this so much with OpenMP, I've seen people ignore OpenMP and then realize that they did need something like this and they did want to use it, and after a long delay come back to it, but get put off by the first results. 2 problems: the standard specification doesn't say anywhere go and look at your memory, right? Because it's telling you some language features, but the things optimizing your memory access, looking at how you're using memory, is not explicitly in the language somewhere, so you kind of got to know that, right? The other thing is that what we tend to forget with that first version is, once you've gotten an OpenMP version, once you've done that work, you have something that's pretty clean and a lot easier to understand than something where you have lots of different threads and complicated interactions. You have a pretty clean code. So the follow-on impact, the code that you can use after that tends to be in a nice form, right? But again, if you think that for any application you can just add 3 directives and you're done, then you may be in for a not so pleasant surprise, right? Usually you have to think a bit more than that. Okay, but that was a great question. Thank you very much. Okay, so it's not perfect. Nothing's perfect. But it does provide a very clean interface, and if the abstractions match what you're trying to do, you can write a good program, and with some thinking about how it's working, you can even get a very well-performing program too. Okay, so the most important features of OpenMP are the directives, and those are, again, sort of structured comments, I tend to call those, which are processed by the compiler to create a parallel code. There is a runtime library. There are not a lot of runtime routines there, but they're quite important you tend to need them quite a bit. So we'll see a few examples of that. It also has some environment variables that you can use to set some of the options to control the execution. And it has, this is I think, a fairly reasonable set of defaults too. Okay, so this is I did not create this. This is a sample set of compilers. I don't think there are any, well, there's GNU's here, but there are more compilers than this, but these are some of the standard ones. So as you see, most of them do provide OpenMP support. You don't have to go and get a different compiler. So that's the good news. You can try this out without having to go and purchase or acquire a compiler other than the one that you're probably using. Most of them today have 3.0 support, or most of the ones that are widely used. There are some of them don't quite have the current range of features. Okay, one thing that's, so when you're trying to actually execute an OpenMP program, so assuming that you've put the directives into your code and you have a compiler on your system, what do? Well, it's pretty easy, actually. So if you have an OpenMP program and you try to run your code with that compiler, so just arbitrarily assuming that the compiler you have is from IBM here, you're going to have to look at the manual and find out what flag or what option to specify to us, which will tell it to look for and implement the OpenMP directives. If you don't do that, it will ignore them. All right? So in other words, the way these compilers work, you have your OpenMP directives in your code. You run your compiler with no change without setting any of the options. Don't be surprised if nothing happens. Okay? So that's another problem that people run into the first time, not knowing that you actually have to go do something there too. Sometimes you have to set a couple of different options, so you really have to look at the manual. There's no standard. So this is actually our research compiler, and it was really just put here to show that the flag's different. So our flag, for various reasons, is called MP and -MP, and IBM has, so no standards in the options that you have to set, unfortunately. Okay, but then it's pretty easy, right? So not a lot of work there. Okay, so the pragmas in C, we've kind of seen an example of this already. So the directives look like this. This is pragma, and this is OMP, mnemonic. A very nasty bug is one where you misspell this because the system doesn't really know what's happened there. So don't expect anybody to help you if that's what you did. So if something's not working, that's one of you. I guess it doesn't happen very often, but one of the sanity checks is just to make sure you didn't misspell this. So in OpenMP, there are a couple of different formats because there are different kinds of comment styles in Fortran, and they're all acceptable. And there's this OMP little thing that, again, the compiler will look for if you have told it to by using the right options. All right. That also means that a compiler that does not have OpenMP in it, and again, there are very few that don't, would just treat these as comments, so it won't do anything to your program. So another potential benefit of this API is that you can have one program that you might run sequentially or in parallel, depending on, perhaps if you're testing something, you might run it sequentially and then run it in parallel mode at another time. Okay. All right, so this is not actually complete, but there are, so I'm going to go very fast through this. We've already seen that parallel directive. There are some directives for distributing the work, which is, of course, very important. I'm going to do a few others first, actually, in this time, so we're trying something a bit different. There are a few that will can have the effect of having just one thread do something while the others are perhaps still doing something else or maybe waiting. We have to worry about different kinds of synchronization. We'll look at just a couple of those today. We'll look at tasking a little bit because that's real important, and we're going to look at a few of the things you can declare data to be, so there is some extra information that you will need to provide with regards to your data. This is not a complete list of features, by the way. It's a subset. Okay, so there are environment variables, and we're not going to actually look at these here in this tutorial because we don't have time. But you can set most of the options that you need, that you'll need to help govern the way your program is executed before it starts, so by using an environment variable, and you can override them. So for each of these variables, there is also a runtime routine that will allow you to retrieve its value dynamically, and another one that will allow you to set it, which will override the environment variable. And I'm just going to pick out a couple of these, sort of perhaps arbitrarily, but actually not entirely arbitrary because I don't get back to them. One of them, this is a rather funny one, and I do want to say this in case you have a problem with it, setting the stack size. When an OpenMP program runs, again, assuming there's anything in parallel, there'll be a bunch of different threads executing. They are executing independently, so they're executing their own code at their own pace, and that means that they can call procedures, right? So they have to have, I don't want to talk too much about compilers because people's eyes glaze over, but these threads have to have their own local stacks. That's where they store their own information, right, so that they can execute their own procedures. And the size of those tends to get set at program start, and it's often too small. So then you can get this nasty error warning that your stack size was too small. Then you may have to go in and set it. I find this kind of ugly because you don't really want to have a user to deal with this, but that's the way it is today. So sometimes those threads just don't have enough space of their own to save all the variables that they need just to execute, and you may have to reset that. If you're a computer scientist, you'll know a lot more about that, of course. Another one that we're not going to get back to is what we call the wait policy. So you get into various situations. Remember, when threads are trying to collaborate to do some work, sometimes one thread has to wait for another one, right, depending on what's going on. And when that happens, so when threads are waiting, there are essentially two basic ways you can think of them waiting. They could be busy waiting, which means that they're incessantly spinning around trying to find out whether they should be doing something again, right? Or they can kind of go to sleep for a bit. And on some systems, busy waiting can be quite expensive. It can consume a lot of resources because it's always testing something, right? So to allow the user to help the system or help the implementation understand, you know, if we have some choices somewhere, if it might be waiting for a while, do you want us to prefer to have the threads polling and looking for work, or would you rather that they sleep for a bit? You can actually set a policy, which is just kind of a general guideline on which of those to prefer. It doesn't mean that it will always do that one, but sometimes, especially if something is waiting for a long time, it will want to go to sleep, and maybe it'll do that sooner if you've said that you prefer it to sleep. Okay, so again, there are these environment routines, and I won't say any more. We're going to look at a couple in a moment that will allow you to retrieve the values of those environment variables or to set them, and setting them will override them. Okay, so very, very quickly, I've got just a couple of slides here on the implementation so that you get a sense of what happens behind the scenes when you're using these directives. Because when you're using the directives yourselves, you're telling the system, I want this to run in parallel, I want the threads to share in this work, but you're not specifying all of the details that you would have to in what we call a lower level model. So how does that happen? This is our compiler, and I don't want to labor this point, so I'll just put these just put these all here. Okay, so obviously the compiler has to better read in those directives. There is actually a very high-level analysis that goes on of your whole program before they're translated at all. In our case, we actually standardize them. That's pretty normal. Then we're trying to do some optimizations before we actually implement the OpenMP. And then there's a phase, this is the critical one, of course, for the OpenMP implementation. It's going to take those OpenMP constructs and replace them by essentially some modified code and calls to our own compiler's runtime library. So it's not the user one in OpenMP, but it's the compiler's system that it uses for managing threads. And then we have some multi-threaded code here. So it's code now with calls to library routines, and we have to do some more optimization. And here's another comment. So one of the good things about OpenMP is as it gets more important in terms of the broad availability of multi-core systems and a very big need for programming models that are reasonably, when I say productive, I mean reasonably high level. So there's a definite space there for people who need something that's not going to require them to write all the nitty-gritty details of multi-threaded code. As there are more users, the vendors work harder and harder on their compilers. So there's a real demand-driven cycle there, right? So more people using this, yes, we're going to put more work into it. It's actually pretty hard to do a good job of optimizing this multi-threaded code. So one of the big problems we had with early versions of OpenMP was that you'd lose a lot of performance just because it was doing this translation and putting in all those function calls. Because if you've taken a compiler class, you'll know that most optimizations happen between function calls, and the amount of code there is much smaller then, right? So it gets harder for the compiler to do a good job of the ordinary things. So as OpenMP becomes more popular, this part is working better. So that's all I wanted to say there. So it's improving. There are a lot of things that can be improved with work, and that is quite hard work, but it does happen. Okay, so the big translation happens somewhere in the middle of the compiler's job to produce object code, and it's going to implement those parallel regions by turning them into multi-threaded code. What happens, I only want to give you a short sense of this because you can look at this on the handout, and if your eyes glaze over, that's just fine. You don't have to really know this. It's good to have a sense of it at some stage. Okay, so here's, this is actually looking not looking too clear to me. Here's our parallel pragma, and this is a very simple parallel region here where each thread is getting its own thread number. So if I have 4 threads, each one will have its own thread number, and they're going to get that and print it out. When this is parallelized by the compiler, what it's going to do is turn that into something that you don't really want to have to read, right? Some stuff in here, but you'll see this code is actually a procedure. So here's what you really need to look at up here. It's going to take that parallel region and do something that we call outlining, which is nothing other than creating a procedure. I'm sorry, I thought I had a comment in here. Okay, so a procedure that's going to encapsulate the code inside that parallel region. And if there are procedure calls in here, there'll be procedure calls in there too. So there's a new parallel region, and we call that outlining. And the other thing it has to do, of course, is make sure that procedure has its arguments. That procedure is going to, or that translated code is going to use what I just called the compiler's runtime library. I'm going to skip over this now, but again, with the handouts, if you really want to, you can go and have a look at our runtime library. There are no standards there, right? So different compilers have their own runtime libraries, their own interfaces, which is a problem if you're trying to write tools. Okay, and it has a whole bunch of routines that actually allow the system to set up and to run threads, to assign work to them, to park them. So the original main program here does all this stuff, and it's just if it gets to this point, it's going to do the fork, and each thread is going to be passed that code and the arguments. All right, so the compiler has to create that routine, set up the argument list, and pass that to it. And by the way, because it might always happen, there may be some reason why this cannot work, why there can't set up any new threads, so it actually has to have a serial version too. So the compiler creates a serial version in case something goes wrong. How do you find out as a program if something's gone wrong? Does anybody know? Yes, that's probably the first indication that something went wrong. But the other answer is that there is no error code in OpenMP. There's nothing, if you used something like MPI and you know that there are things like error codes that doesn't exist here, you have to check, right? So there is a little routine that you can use to actually find out. It will tell you yes or no answer, was this executed inside a parallel region. So you have to, in other words, be active. All right, so there's the fork. That's right, this is actually, because it's a parallel, this is actually a pointer to the area that the thread can use for its variables. Okay, and the serial bit. Okay, so the idea, of course, and this is supposed to be sort of motivating, is that that we don't, that would be very unfair to call this Pthreads, to equate this as Pthreads. But the idea is, of course, that you want to avoid this. Okay, so I'm going to just go very quickly through a few things here because I want to get to the work sharing part that's arguably the most important piece of this. One thing, this is historically perhaps more interesting than now. We can have what we call orphan directives in OpenMP, and all that means is that if you have a parallel region, you can have procedure calls in there, and inside those procedures you can have OpenMP constructs, even though you can't actually see the parallel region there. Seems kind of like a no-brainer today, but there were earlier attempts to create interfaces like this that didn't have that power. So it's, again, today, we probably shouldn't even bother saying so anymore. Okay, so here's a very simple program. All right. We have an include file at the top. We have something here which is getting the number of threads that will execute the program. You've probably set that in an environment variable, so it's retrieving the number. All right, now we have the parallel region. So again, we don't have to do too much more in some cases. And in this parallel region is starting here and ends down here. So that part is going to be executed by a team of threads that will share in the work. In this particular case, what they're doing is real simple. So these are all very simplistic except for the last example. Each of them is going to get its own thread number. Okay, so if we look at the output here, the master thread of a team always has thread number 0. So you always know that's the master. The other threads always have numbers that are consecutive, so starting with 1. So here we have 4 threads, and they are 0, 1, 2, 3. Okay, so you know that. So if you take the number of threads, which in this case would be 4, you know that the largest thread ID is going to be 4 minus 1, which is 3. We can all figure that out, right? Okay, so we know those numbers. And one way to use OpenMP is, in fact, explicitly to assign work to threads based on their numbers. That may not be, well, very elegant, but sometimes it's very useful, and you do have a simple interface. And you have one piece of code. So you can do it if that's what you want to do. So again, these are simple, but they're pretty powerful because you can actually use them to assign the work. Okay, so each thread is getting its own thread number, and it's printing out, hi. So it's sort of like a hello world here. And notice again, you probably know this already, but the obvious that there's no guarantee on the ordering of that output there because these threads are executing at their own speed, and so if you run this different times, you'll probably get different threads being a little bit faster each time and just beating the others to it. Now we have a barrier. So OpenMP does not have a lot of synchronization mechanisms. So the most common one is a barrier where all the threads, right? The threads wait at the barrier until everybody reaches it, and then they can proceed and do whatever comes after it. So in this particular case, you're enforcing a barrier because you want to have, sorry, again, a nonsense example, but you want to have this printout or this line being printed out after all the others have done their execution. And we've ensured that the master thread does it here by having the thread with ID 0 actually execute that line. Okay, so that's, if you like, low-level programming of a very simplistic kind. Okay, and here we have the join at the end here. All the threads have completed their work. The parallel region concludes. Okay, the Fortran version, I have chosen mostly to use C here, but if you look at it, it's pretty similar. So if you look at especially the constructs, they do pretty much match. So one thing that's slightly different in Fortran is that, or it is different, is that just because of the nature of Fortran, that many of the constructs have an end construct. Right? So you put something in at the start, but you have to mark the end. With C, we don't have that problem. Yeah?
Yeah, I wanted to ask you this in the beginning. But
oh, sorry.
So if I notice you declare none here share,
Mm-hmm.
And that I guess is to get access inside that section. What happens if you don't declare it anything? You do not get access at all?
That's good. I have a slide on that somewhere, but we can do it now. Okay, we just don't worry about that. So there's one thing that we'll just jump over those slides when we get here, but this is as good a time to say it as anywhere. There's several things that are important in OpenMP programs. One of them is having this parallel directive to govern to describe what should be executed in parallel. Another very important thing that you have to do is say how the data is going to be used. So OpenMP, in principle, you could have shared values of everything, but in practice that doesn't work too well. In fact, there are a couple of things where that's really awkward. So in practice, OpenMP provides shared, or allows you to specify variables to be shared or private. And there are a few more options that you probably know about. We'll get to those. So typically, if you have an OpenMP program and you have a parallel region and you say nothing about how your variables are going to be used, they will be shared. That's your basic default. So the variables, there's one exception to that, and we'll show it later. But the variables in here would then be shared among the different threads. So if you have, let's say, an X in here, it would be shared. This TID would be shared. That's, in this case, a very, very bad idea because, in fact, they're all the threads. This would be something that you absolutely would not do. It's actually not legal, but the system's not going to stop you from doing it. Each thread needs to have its own value of this thread number, right? They're going to go out and call that function, but they will each get a different result. So they need to have their own copies of this thread ID. It's very easy to enforce that. When you are starting this up, you'll say, or just declare it to be private. So this is like a data declaration. So you declare variables to be shared or private. It is good practice to explicitly declare all variables to be shared or private. In other words, to write down and not rely on defaults. And the reason for that is that one of the most common errors that you get in programs is somebody actually thinking that a variable is, say, private, but not noticing that they didn't explicitly privatize it, so the system's treating it as shared, right? Very nasty little bug. So usually when you're writing a program and creating a parallel region, you need to look at the data and think about, should this data be shared or should it be private? Sometimes it's a performance issue. Sometimes it's just can work a little faster if you have private variables. There's a sort of a trade-off there, by the way, too, because the more private data you have, the bigger your memory footprint. So you don't want to arbitrarily make everything private, but it does tend to enhance your performance. So some data will need to be shared if they're working together in a normal program, but you will want also some private copies. So this one is private, and this numt is shared, and that is holding this value of the number of threads in here. So that's shared. They can all see that. Not that they're actually doing anything with it here, except for thread 0. Yes, sorry. Should I go back to this? Right. Okay. So I don't think too many programs actually want to have a barrier like this, but sometimes you do. So a barrier, again, is a construct where all of the threads, remember that when the threads are executing this, so all the threads that are in the team, we call this a team executing the parallel region, they will all execute this line of code. They will all do their printout, but at slightly different speeds, right? And in particular, if there's this one print line, there's a bit of ordering going on here, which in this case is arbitrary. And when they've done this work, so each thread works at its own speed. And you do observe variations in this. So sometimes the operating system kicks in and does something somewhere, and one really slows down. Can even happen. So they will work at slightly different speeds, and then they will hit this barrier. And all of the threads have to wait at the barrier until every single thread in the team that's executing this reaches that. So once they've all reached the barrier, then they can proceed. Okay? So at this point, again, this is a pretty arbitrary example, obviously, so there's not a whole lot of value in this, except here that we've made sure that it's the master thread that's actually going to print this out, and it does it after the others have done their printout. Okay? Is that enough? Yeah. So there are actually barriers, quite a few barriers in OpenMP programs because they are implicit in a lot of other constructs. So in particular, when you end the parallel region, there's a barrier there, right? All of the threads complete the parallel region, finish up all of their work, and then the master thread can go on and do some more sequential work. Right? So there are several places where barriers actually occur, and I'll try to remember to tell you them. Okay, so this is just, I'm going to zap through this because I need to do some other things and wrap up. Okay, so forks, they're all going to do their work, so it looks like they're at the same time here, and they're sort of at the same time. They all wait at that barrier until they've all gotten there, and then only that thread with ID 0 continues. Okay, I'm going to go pretty quickly through a few things and just mention them here so that you know things are there, and if you want to use them, you can look at the slides, but also look at the spec. First of all, sometimes there's not enough work in a piece of code to make it worthwhile to execute it in parallel. So you can actually have a clause that will test that. You have to supply the condition, of course, but if the condition is false, then you won't execute it in parallel. This is where I was going to talk about the data environments or talk about the shared and private, so we kind of did that. So I'll just mention the other options very briefly here. You can actually change the default, but normally the default is shared. So if you don't say something, the variables are shared in a parallel region. Again, it's very good practice to say explicitly for every single variable what it is. It's a bit tedious, but very valuable. First private simply means that it's going to be initialized by a variable with the same name in the master thread, so in the thread that's starting up the parallel region. Last private means that the very last value of a private variable will be transported back outside of the parallel region. Thread private, just jumping to that, we'll talk about reduction in a moment. Thread private I think of it as being actually a way to use common blocks inside OpenMP. So if you're interested in that, check it out and have a look. You can actually use something that's kind of like common blocks. All right, so here's our example here. This was where I was going to talk about that private and shared, but we kind of did that. So, and again, Fortran and C are pretty similar. This is something that we could probably spend 15 minutes on, but we won't because we don't have time. I do have to say something, though. The problem that all of the shared memory programming models have is that they say, oh, everything's shared. But in reality, there is cache that is not shared, right? So threads will be associated with some part of the machine, with some core, and there will be cache associated with that core. And there are going to be multiple caches across your system. And they may, so that means that there is a kind of a space in memory that is not truly shared. Another issue that you can have is that if a thread has just assigned a value to a shared object, that value might still be in a register somewhere, okay? What if another thread wants it? Okay. So, in fact, that means that there are a few rules on how you can use OpenMP, or things that are legal and not legal, and essentially you're not supposed to, and I doubt if people do this willingly, or at least if they do it, then they know that they don't care. You're not supposed to have race conditions in OpenMP programs, and a race condition can occur if you have a piece of code with some references to a shared variable, and one thread is creating a new value for it, and another one is using that value, and you don't have any ordering, right? If you have a piece of code in a parallel region where one thread is, say, defining a new value for A, and another thread is using A, you have to be careful to specify an ordering, all right? You have to make sure that it's not arbitrary. Because if it's arbitrary, you don't know which one's going to be faster. You don't know when the new value of A is going to be written back. So you get what you get. All right. There are quite a few different places, however, in an OpenMP program where the threads have to do something that we call flushing, which I'm sure many of you know about. And that's simply they have to basically write all of their data back to main memory. And that means that it's available to any other thread that accesses it. And so that's kind of important. OpenMP actually has a flush, and if you want to use it, I would strongly encourage you to look at examples of how to use it, because it's one of the things that it's easiest to get wrong, right? Flushing writes a thread's variables back to data. It does not pass them on to another thread, right? So it doesn't imply that two threads synchronize. It just says that one thread is writing all its stuff back to memory, and you can use it to do a very call it low-level kind of synchronization, but you have to look at it a little bit and understand how it's used and what it means to get it right. Okay, so OpenMP threads do have to write things back to main memory, but they don't have to do it all the time. Why? Because of performance. If they were always incessantly writing everything right straight back to main memory, then the performance would be hard to achieve. So again, just to kind of recap, the threads are all operating in this wonderful shared memory, but they have their own local caches and some shared value. If this thread down here has updated something, it could be potentially here and not in the other caches, right? So for a little while, this thread might have the different value for some shared data that has not been transported back to main memory. So you have to know the rules there. And again,
Question on that.
yes.
Does the flush also clear the cache for those variables in the other thread?
No, it's just between one thread and main memory. That's the problem. All right. So you have to be a little careful when you're using and not to assume that. So let's say this one's updated A and this one wants to use the new value. Flushing this back to memory doesn't write it into here. That's the problem. So this one has to do a flush as well. So it's a little bit more complicated. It's not. Once you get the point, it's not hard to use, but it's very easy to get it wrong. Yeah. This one, if you don't do anything, it doesn't know anything about it, right? So this isn't as bad as it sounds because the standard implies a fair amount of flushing. A lot of the constructs require a flush. So in other words, if you have a construct, the typical thing was that they will all basically write everything back to memory and, in fact, get new values at once, execute the construct, do the same thing at the end. So it's only inside. There are certain places where you could potentially have a problem, right? And the worst one is actually, I'm sorry, I guess I'm making a mental note to add another slide about this. I was hoping to do it real fast because it's just kind of hard to talk about. The biggest thing that you should not do is if you have a piece of code in a parallel region where there is no synchronization, so no constructs that imply any kinds of barriers of any kind, and one of the threads is writing a value, say A, and another thread, then you don't want any other threads using that value of A. Okay? So you should do that. You need to have some synchronization there. We'll look at a couple of ways of how to do that in a moment. Okay? So I'll try and race to get that too. So that it's not a problem with no solutions. It's just that you need to know that you have to have a solution. So we'll look at that in a moment. All right. I'll just jump over the barrier. Okay. This is actually one of the ways in which you can bypass that problem. So here we have what we call a reduction operation. So everybody know what a reduction is? Obviously, when the typical case is when some value, or some perhaps a product, minimum or maximum, is being computed, and each thread is contributing a portion to that one value. And here we have, let me see. So we have the reduction variable is I. So if we look at here, we are initializing I at the start just to 0. This is just a very simple sum here. And in fact, each thread is going to, okay, so the parallel region will be started. Each thread in the team will get its thread ID, will add 1 to it, so a trivial operation in this case. And it's going to increment or add its component to that I, right? All right, so what happens here? So if this is a shared, is it shared? Is I shared? Well, that's a nasty question because it's actually a reduction operation, but in principle, it's not private. Okay? So it's not a private object in the normal sense. If we were to say nothing at all, I would be shared. And what would happen then, so if we forget about that, just pretend we don't have that reduction there for a moment, then I would be a shared variable. So each thread would be creating, this is private, it's getting its own thread ID, adding 1 to it, so thread 0 will have 1 here, thread 3 will have 4, and so on. We'll update this. What's happening? Again, if that was shared, each of them would be writing to the same variable. It would be exactly the situation, well, not quite the situation I described before, but something very close to it. Because they would all be trying to write to the same object. And what would happen? Well, in a good case, one arbitrary value would write to you. It could even potentially end up with garbage in that location, right? But we'll probably get one of the values here, so maybe the very last one to write a value. Values. Okay? So in this case, when we want a reduction, we would really like to have, the idea of having a reduction is that you don't have to rewrite this code, right? So you can leave this in here, but you declare this as a reduction variable, and what the implementation has to do then is, in fact, it's going to let each each thread have its own copy of this. You just don't have to say so. It's going to create a local temporary variable. Sorry, I'm just moving in and out of something here. Create its own temporary variable to hold that local value, and at the end of the operation, it's going to accumulate them. And it's performing the reduction. Okay? Reductions are extremely common. This is actually, I think, perhaps not such a great example because it's a bit too simplistic. But the idea of a reduction is that you can have something that you don't have to create as a private copy. And oops. See where I can stand in a better place. And you can allow the
the connection to your microphone is intermittent.
I'm so sorry.
That's what's causing the trouble.
Okay. I wonder if I need to put it somewhere else. Is this helping at all?
How's it matter?
Well, I guess I can hold it. Does this help me? No, so it's not. Oh, okay.
It's where the
I'll tell you what.
plugs into the transmitter.
Yeah, yeah. Okay. Let's do without it because we're kind of almost out of time. So, and I'm struggling a little bit to explain this. I notice. I think I need to add a slide here. Okay, so reductions, I hope, are pretty simple. But if you wanted to implement OpenMP, or at least if you did not have a reduction variable, you would have to rewrite a piece of code with a reduction variable so that each thread has a private value, and then you have to collect those private values, and you would have to copy them into shared data or use different shared data. And at the very end, you would have to explicitly add them up, which is kind of ugly. So OpenMP actually has something called a reduction, which allows it to do that for you. All right? So in other words, you can keep your shared object is essentially shared, and the implementation will create local variables to accumulate, if you like, the local values, and it will implement the update at the end. And if it's well done, that's a lot faster than a typical hand-coded implementation. So I have to I'm sorry, I'm trying to go too fast over some of these things, which is why I'm getting a little bit, finding it a little hard to describe. This I do plan to skip, but I didn't take it out of the slides because I want you to be aware of this. This is something that I think will be important in future. OpenMP allows parallel regions to be nested. That means you can create some parallel regions, and you can create another set of parallel regions underneath them. Levels, you can control the number of levels. They added in 3.0 a bunch of features that will allow you to actually uniquely identify every single thread inside here if that's what you want to do. So this used to be a feature that didn't have any teeth. It's getting a lot more muscle, so to speak, from the latest standard, and I think that will grow. This sort of implies that they all have to be the same and have to have the same number of threads. That is also not true. Those different parallel regions that are created here, the different threads and teams can have different defaults, different settings. So you can potentially use that to actually divvy up the work among a set of threads, and then send different teams of threads off to do different things. So this has become, people have recognized that this could be quite important, and so it's getting more powerful as a construct and will be more useful. Okay, so this is where I did want to go. This is sort of, thank you, all right. Let's see if this helps. Great. Yeah, thanks for pointing it out. I didn't quite know what was happening before, so okay, good. Okay, so this is actually I'm going to do this very quickly. This is incredibly important, but it's also kind of easy. So without actually distributing the work using high-level constructs, we have a somewhat low-level programming model. So we can actually share or distribute the work among different threads using those thread IDs, as we've seen, but there are easier ways to do it. The most common one is actually using parallel loops, so a for or a do loop in Fortran, and simply parceling out the iterations to the different threads, so getting each one to do its share. This is extremely common and is, I think, what most people use OpenMP to do. And so in other words, we have a set of loops, and we're going to want the system to, or the implementation to figure out which iterations each thread actually has to execute. So again, we don't have to do that, right? We can just say that it's going to be done in parallel and using our pragma. So this case, it's for, or it's OMP do for Fortran, OMP4 for C and C++. And we're putting that, prepending it, if you like, to the parallel loop. And the implementation will then map the iterations to the executing threads in an even manner. If we don't say anything about how to do that, it's going to select its default schedule, and that is nowadays invariably what we call a static schedule. It's going to take a chunk of iterations and give them to thread 0, another chunk, usually hopefully of exactly the same size to the next thread, and so on. So contiguous chunks of threads. If we put no wait here, then at the end of this parallel loop, it will go ahead and in this case will print out the value that it's assigned to. If we don't have that no wait, there will be a barrier here at the end of the loop. All right, so it's another place where there is some synchronization. Barriers flush everything out and update, so you have this memory synchronization going on here too. So if you want that, you have to leave it as it is. If you don't need that, you can put this no wait, and threads will just continue. Okay, so usually very straightforward. Okay, and in Fortran, again, it looks pretty similar. So here we have the do, and we have the end do. All right, so again, with Fortran, you tend to have an end construct as well. And the no wait, in this case, would come at the end, so if you want to use it. So no wait just says, I don't need to do any synchronization at the end of this loop. Just keep on working. If you don't have that no wait in there, so the default, if you like, is to have a barrier here. And that barrier makes all of the threads wait, and it does update all of the variables. So all of the shared data is updated and made available to all threads at that point. Okay, so what if those iterations don't have the same amount of work? Then we have to get involved a little bit and think about exactly how we do want the threads to be, or the iterations to be distributed to the threads. So there are a few other ways of doing that, and again, I'll just quickly say that they're there. Static is the fastest one. That's one contiguous chunk of iterations to each thread. Dynamic as a situation where you can control how the number that they start with, but each thread will go out and grab a set of iterations. When it's done, it will go out and grab another set. So if one lot goes particularly quickly, thread 3, for example, might do its set and go out and grab another set before anybody else is ready with its first one. So if, in practice, if you have something with a variation of workload, sometimes it's good to actually try out different options and find out whether the dynamic one is the right choice. So it has a few more overheads because threads have to keep on going out and grabbing sets of iterations rather than just knowing their own set. But if the workload varies a lot, it can be very beneficial. Okay, so again, if you want to, we said that OpenMP do and the OpenMP for before, and if you want to, you can give it a schedule, which means an assignment of loop iterations. Okay, there are sections. I'm going to say this just very briefly. Sections are, it's another very old construct, another, if you like, a historical way of assigning work. A section is actually a sequential piece of code. So if you have a sections construct in OpenMP, you can have, this one is, the problem with sections is that they're rather rigid. So this one has 3 pieces of work in it. 3 threads can execute this. 1 thread can execute this one this, and one this, all at the same time. If you only have 2 threads, one of them will do this, one will do that, and whoever's done first will grab this one. All right? But there's no more work there. So if you had 10 threads, 7 of them would be idle. So it's just this one. Tasks, the last thing I want to get to, very important. Just let's see, just go to this one, I think. Tasks, in part inspired by Silk and other programming models, if you're aware of them. A task is a piece of work that is created, and at least in principle, you create the tasks, you package the task, and you put it in a pool of tasks for execution. And so there's a bit of a disconnect, if you like, between the time the task is created and when it's executed. You don't know anything typically about the order in which different tasks are executed, and you may or may not, in OpenMP, you don't normally know exactly where it's going to be executed either. So tasks are pieces of work that will be created and will be executed by a task, by a thread, I'm sorry. And so the data is actually captured at the time of creation, which means that by default, this doesn't have something in it that I could show you there, but values. Okay, sorry, we do have this one. Values are actually captured at the task of creation. So if you want to, if you're following a list structure as we're doing in this one, you need to know actually which node is being processed at that time. So you actually have to record that value. Okay? So if you're used to using tasks in another construct, OpenMP has them in a fairly simple way, right? You create your tasks, they're executed, and sorry. All right. So I just want to go the wrong way. Okay. And they will, so the system will continue to execute them until it reaches a barrier. Okay, so if you create a task and create other tasks, you could end up with a whole bunch of tasks in your system that need to be executed at a barrier. So if there's a barrier in your program, all of the tasks must be completed. Right? So you can't do anything more until you've had the barrier. There's also a task wait directive, which will cause the tasks immediately preceding it to complete. So there's an extra piece of synchronization for tasks. Okay. All right. Very briefly, I wanted to do one other thing, and then we're done. And that is simply mention that we have more more synchronization constructs in OpenMP. And one of the other ones, this is a very, very common operation in, or at least a traditionally very common operation in shared memory models, is to have a critical region or a critical section. So we call this a critical region. And in a critical region, we may have updates to shared data. And we want to protect them because, remember, we have to make sure if one thread is updating a shared value that others are not trying to read or write it at the same time. And with critical, we can do that quite easily by simply by using this pragma. The point about a critical region or critical section, as kind of traditional name for them, is that only one thread can work on the code inside the critical region at any time, but we don't know the order. So if we look at this piece of code here, right. So this is inside a parallel loop. We've got multiple threads executing it. They're all going to update. So this is sort of nonsense code here. Updating C of 0. We don't want them to do that first of all, we don't want to, so they're incrementing it. We want to capture all their updates, but we don't care what order because we're incrementing, right? So it doesn't really matter which order they happen in. So with a critical region, the very first thread to reach that region will enter it, will do its update, and will execute the critical region, and will write its values back, so that will happen. Then the next thread will enter it, do its update, write its values back, and then the last one will do it. So we don't care about the order. We just need to care about the fact that they are not doing it at the same time and that the values are properly written back and retrieved. Right? So if we think about that, flushing happens at the start and at the end. Right? So everybody gets the current values. So that's a very easy way to do that. You can have multiple critical regions with different names, and that means that they don't collaborate. They know that they're distinct ones. So here we can see that one thread is working on one critical region and another thread is working on another critical region, and they're quite different ones, so they don't interfere with each other. You don't want to have too much code in a critical region. Are you okay if I try to do this quickly? Yeah. Okay. So yeah, this went over time. I should have skipped a few things, I guess. All right. So very, very quickly, just one example, so you can look at this later. I'll just this is I know these are all kind of simple examples. So if you remember the pi computation where you're summing these little rectangles, I'm just going to go through this real fast and let you have a look at it later. There's a couple of different ways of writing this in OpenMP. This one's real simplistic, and there's one that's actually a little better. So first one, we're actually getting the number of threads that we've actually defined at the top here. We're creating a parallel region, so we're going to have a master thread, the initial thread coming in. It will fork threads. We've just got two of them in this case. Those threads will work on this. We've got several private variables declared. One of them is going to be used to hold the thread's thread number. One of the threads, we put a single on here that just says one thread, but we don't care which one is going to execute this line, which is getting the total number of threads. So it's shared data, so they can all retrieve this, but only one of them is going to actually call that operation, because we don't want them to all go and do the same thing. All right, and then we have a loop, and we've manually actually partitioned this loop out. So each of them is using its own thread ID to figure out which set of iterations it has. You can do all this, right? It's kludgy, but you can do it, right? Just using those IDs. So each one will do a set of iterations of the loop, and at the end we're going to have to sum up the different variable values, and that's outside of this parallel. So that's one way to do things, but it's not a very good way because it's not really using the power of OpenMP very well. So one minor thing that we can do to improve that is simply to use a critical to do that sum, right? So we have a critical there. Each one is adding its own local value now, its own local contribution into the overall sum, and they're not clobbering each other. But of course, we have a much better option in OpenMP, and that is to look how much shorter this is. We can use reductions, because that sum is also nothing but a reduction operation, because each thread is contributing its portion, right, to the overall integration there, so the overall sum of the rectangles. And the other thing, of course, that we can do is we can have a parallel for loop, so we don't have to go and compute all of those things ourselves. So in fact, one thing we can do in OpenMP that's sort of like a little bit of an extra, so I didn't talk about it, is you can combine the parallel loop and the for directive or do directive. So we've got here just one line, pragma OMP parallel for, and that's a parallel region that consists of this single parallel loop. And now we're going to rely on the implementation to do all the mapping of the iterations to the threads. We've got a private variable here, and we've got reduction. So the individual contributions are going to be summed into this value, and we're going to leave it up to the implementation to do the dirty work of making sure that each thread gets does its own contribution, and that they get combined in a sensible fashion. We don't have to do it anymore. Okay. So, and here we're actually setting the number of threads here using this variable. Okay, so that's all we need to do, and we have an OpenMP program. And as you see that we have, going back right to the start, we have a minimal intrusion in terms of the lines of code. Okay, I'm going to leave this for you to look at later on. Performance tips, very important, of course. So try to have big parallel regions. You have to think carefully about what should be shared and what should be private. Careful when testing. It's a good idea to exploit the fact that you can iteratively insert things by putting some things in and testing and making sure that everything's correct before moving on. Okay. It's busy. I mentioned this at the start. The Architecture Review Board is working on a whole lot of different things.